Here I will show you how to apply the Lagrange multipliers for the solution of a flow problem or for flow in porous media with the comsol model to be able to calculate accurate fluxes. So here we see the comsol 5.1 web page, or I should say the application page. Choose the model wizard, and the application I'm going to do is we're going to do a 3D model. We could do it for 2D axisymmetric 2D model, 1D axisymmetric, or 1D, but we'll do it for 3D. So choose 3D, and here we'll look at porous media flow, and for simplicity I'll use the Darcy flow model. So we add that. Looking at the study, we'll do steady state, and with that we have the model set up. The geometry is going to be for a cylinder, just with radius of 1 and length of 1, so we'll build that. Here's our cylinder here on the right hand side. For Darcy's equation, the fluid properties, we'll put in the density usually defined would be 1,000 cubic meters, or 1,000 kilograms per cubic meter. We won't set the dynamic viscosity because we're going to set the hydraulic conductivity, and for that we'll use 5 times 10 to the minus 4 for the hydraulic conductivity. Now the boundary conditions are going to be such that we specify a hydraulic head at the top surface, hydraulic head at the bottom surface. The radial boundary is going to be impermeable. So I have one-dimensional flow. What we're going to demonstrate is the use of the Lagrange multiplier to calculate the fluxes and show how the fluxes calculated with that are more accurate than the normal Darcy fluxes that are calculated after the solution is derived. The Lagrange multiplier is calculated immediately at the time when the solution is derived, and it satisfies the actual matrix equations that are used in the finite element solution. For the initial values, we'll just put a value in here. It's not really all that important, but we'll put a value of 0 for the initial value. Since it's steady state, it really won't matter what we put for the initial value. Okay, for the mesh, I'm going to start off with just a normal mesh, and using linear elements. This is something that we'll look at here. That is, if we go to the component, we can choose which type of elements we're going to use. Automatic, the default is to use a linear element. The element, these descriptions here define the Lagrange polynomials that are used to define the variation of pressure between node points within an element. So if we choose linear, it just means that the pressure varies linearly within any element. In this case, they're tetrahedral elements, so the pressure will vary linearly within the tetrahedral element. We could choose quadratic, cubic, quartic, quintic, sextic, or septic. So first order, second order, third order, and so on. The higher the order, the more accurate the solution will be, the fewer the elements that will be required. And I'll show you actually that by choosing a higher order element, we can get away with fewer number of elements, and we'll get a more accurate Darcy flux, even without using the Lagrange multiplier approach. Alright, so we'll start off, we'll use the linear element for the solution. We need to define the boundary conditions. Well, of course, by default, the radial boundaries are impermeable. Here we'll define the boundaries. Go to Physics button here, and we'll choose the boundaries. So we're going to set a hydraulic head, and we're going to set the hydraulic head on the top surface to be equal to 1 meter. And mistake there. Then we'll add another one for the bottom surface, and for that one the hydraulic head is set to 0. So with that, you can go to study, set the initial condition, which is of course a condition of 0 hydraulic head everywhere. For this, we're going to define the slices as being, instead of vertical, we're going to make them in the XY plane, so that we've got that. So now if we derive a solution, we can see that the hydraulic head varies linearly with elevation. Now these values are in pascals, and I'm going to convert that to hydraulic head in meters. Alright, so now we have the hydraulic head plotted in meters, varies between 1.0 and 0.0. Alright, so here we'd like to be able to define the fluxes at the top boundary and the bottom boundary. For that, we can go to the results, and we can come up with some derived results. And what we're going to do is do a surface integration of the flux across the top boundary and across the bottom boundary. So here's the surface integration variable, and what we want to do is we want to choose the Darcy flux, which is in the vertical direction. That would be dl dot w, and we're doing a surface integration across the boundary, and we're doing it for boundary 4. So doing that, we can evaluate that, and you can see that the flux in cubic meters per second is minus 0.0015616. And theoretically, with the unit hydraulic gradient as we have, and a hydraulic conductivity 5 times 10 to the minus 4, with this cross-sectional area of 3.14159, that is basically equal to pi, the flux should be minus 0.001577, and not the number that's given there. Now this has to do with element size and so forth. So I'll demonstrate here what happens if we were to use higher or larger numbers of elements. And so we can go to the mesh, we can generate a more coarse mesh. Here we had a normal mesh. We go to a not normal but to extra fine mesh. We generate that mesh, which of course requires a bit of time, and then we go back and we solve this. We get a solution for this case, and it takes a little bit more time, of course, because there's a lot more elements, a lot more node points. So this is probably about 400,000 elements, or 400,000 node points. I hope it actually solves. I think it will. And when we get to this kind of discretization, we'll actually get a fairly accurate answer for the boundary flux. So again, we go back to the surface integration. We evaluate that, and you can see that we're pretty close, 0.00156696. It should be, as I said before, 0.00157707. So we're not quite there yet, and that's with a very large number of elements. Now we'll go back to the coarser mesh, that is the normal mesh, generate that again. And instead of linear elements, they're going to use quadratic elements. It's going to be amazing to see the effect that this has on the solution. Okay. By using quadratic elements, we do increase the number of degrees of freedom, number of elements, and so forth, or number of nodes, but the number of elements is still the same number as we had before when we did that with linear elements. The number of nodes is greater because each element has more nodes to it for the interpolation. I'm going to erase the table here, just clear the table because I want to be able to see something when I go to do the calculation. Now we'll calculate again the surface integration. And you notice 0.001708. So with the same discretization we had for the linear elements, for the normal discretization, we're getting a very good answer by just simply using quadratic elements. I could go to cubic elements here, and presumably I'd get even a better answer than I got before. We'll see what happens here. I think the answer doesn't actually improve all that much. Yeah, it's basically the same. So using higher order elements certainly helps. Our geometry here for this system is very regular. There's no weird corners or anything like that. But even so, we see that the Darcy flux does not provide a very good answer for the linear elements when unless we use a very large number of elements. Now what we'll see is by using the Lagrange multiplier we'll get a much better answer. It will not necessarily be exactly the answer that's given by the theoretical calculation or analytical calculation. But the one thing about the Lagrange multiplier approach is that it will give an answer that's consistent with the rest of the calculations, whereas the Darcy flux calculation is not consistent. So you cannot expect to be guaranteed that the Darcy flux calculation is going to give you boundary fluxes that will yield conservation of true conservation of mass. That is, rate of change of storage is equal to the net flux through the boundaries. With the Lagrange multiplier approach, we will find that, or I will not demonstrate that to you, but it is true that the fluxes that are obtained with the Lagrange multiplier will be exactly correct with respect to that conservation of mass, and that's why it's suggested to use that as opposed to using the Darcy flux calculations. So let's see how we actually implement the Lagrange multiplier. And there are actually two different methods that could be used to compute accurate fluxes. The one that we're going to use is the Lagrange multiplier. We'll talk more about the other approach at a later time because I've never actually implemented that other approach. But let's go to the upper boundary, which is this boundary here, where we got the hydraulic head set to equal to 1. Here we're going to set a constraint, and that constraint is going to be what we're going to call, we could just call it the independent variables, individual independent variables. We're going to use a weak constraint. Basically what this does is it's going to include an additional parameter or an additional variable or additional degree of freedom in the matrix equations. On the equations that happen to correspond to the nodes that are on the boundary value is specified to be a given hydraulic head, in this case 1.0 for that boundary. That equation really is not needed in the solution because it's got a specified hydraulic head value. But within that equation, the finite element equation, the discrete finite element equation associated with that particular node on the boundary, there is a term that is the net flux at that point. That net flux is the flux, the normal flux across the boundary. And by implementing this weak constraint, the weak constraint is the Lagrange multiplier, which happens to be that flux. the finite element solution will compute that flux and will output it. That will be able to then integrate it over the surface and give us the accurate mass conservative net flux across the boundary. So by setting that value, and we'll do that also on the bottom boundary, because we have to do it on both boundaries. Here at the bottom boundary, which is boundary number 3 in the lower part, we'll set the same weak constraint. Okay, so now we're set, and all we have to do is, now we're going here, we're using we want to use the linear element, just because we'll go back and I mean, this is going to give us good result, but it won't be perfect, of course, unless we refine, but we don't have to refine as much as we do if we're using just the Darcy flux. We are also using here the normal mesh, so it's the coarser mesh. Alright, so we go here and we will solve this. Of course, the solution for the hydraulic heads does not change. But now let's look at the surface integration. I'm going to duplicate this, so I'm going to have a second one. It looks just like it, but now instead of using the Darcy flux, I'm going to come in here, I'm going to choose from this what's called the P.lm, which is the Lagrange multiplier for pressure. So this is the name of that variable within the comsol. The units here are screwed up. This should be, this P-lm should be meters cubed per second. So I'm not sure why it's not able to find what the correct dimensions are, but that's what that integration should be. You don't have to do anything with any of this part down here. Alright, so now what we're going to do is integrate that Lagrange multiplier, which has a value at each of the node points on the top boundary here. If we were to look at this, the grid, at every intersection point there's a node. At every node there will be a value of that Lagrange multiplier. Alright, so now I'm going to clear this table again so we can see something, and we'll evaluate that. Alright, so now the value that we get from that is the actual flux across that boundary. Now we got to recall that this is not a volumetric flux, but it is a mass flux, because if we go back and look at the Darcy's law, the flux is rho times u. Rho, of course, is the density, u is the velocity, the Darcy velocity. So rho times u, rho is 1,000 kilograms per cubic meter. Rho, it would be the velocity, Darcy velocity in meters per second. So this value that we get from Lagrange multiplier is the product of the density times the velocity. If we want just the velocity, we divide that number by 1,000. So this should actually be kilograms per second, and not meters per second, or not cubic meters per second. And we can see that the number is 1.5637. It theoretically, for the unit hydraulic gradient we have in here, it should be 1.5707. And we can get that, of course, by simply going to quadratic elements, or we could increase the number of linear elements. Let's just go with the quadratic elements for right now. Do this again. So you get 1.5708. So we're right on by using the quadratic elements. I could have just increased the number of linear elements to get this. Again, this is not exactly the right answer right here. This 1.5637, as I've already mentioned. We can increase it by improve it by increasing the number of elements. But either way, the one thing that's important about the Lagrange multiplier is that the value that you get from that will be the one that's consistent with the mass balance for the finite element, overall finite element solution. The Darcy flux quantity that you would use if you were to use that number will not be consistent with that mass conservation. And so that's why it's important to use Lagrange multiplier as opposed to for calculating the flux, as opposed to using the Darcy flux, because the Darcy flux calculation is not consistent with the overall matrix solution. And with that, we'll stop at that point.